Download this code from codegive.com, link in the description below. OK, let's dive deep into Andrew Kelley's practical data-oriented design, DOD, principles. This will be a comprehensive tutorial with code examples in C, as that's the language most often associated with DOD, and explanations to help you understand the core concepts and how to apply them in your projects. What is data-oriented design, DOD? Data-oriented design is a programming paradigm that prioritizes the organization and transformation of data for performance. Instead of focusing on objects and their methods, DOD focuses on how data is laid out in memory and how algorithms process that data. The primary goal is to optimize for cache utilization and minimize memory access latency, leading to significant performance improvements, particularly in performance-critical applications like game development, simulations, and high-performance computing. Why data-oriented design? Modern CPUs are incredibly fast, but memory access is comparatively slow. Data must be fetched from memory, RAM, into the CPU's cache hierarchy, L1, L2, L3, before it can be processed. If the data is not in the cache, a cache miss, the CPU must stall while waiting for the data to be retrieved from slower memory. DOD aims to minimize cache misses and maximize cache hits. Key principles of DOD. 1. Structure of arrays, SOA, versus array of structures, AUS. AUS, array of structures, a traditional object-oriented approach where data related to a single entity is grouped together in a struct or object, and then an array of these structs is used. Problem: when iterating over entities to, say, update the positions of all entities, you are fetching the health and team data into the cache even though you don't need it. This wastes cache space and increases memory bandwidth usage. SOA, structure of arrays, data is organized so that each attribute of all entities is stored in a separate array. Benefit: when iterating over entities to update their positions, you only need to access the X, Y, and Z arrays. The health and team data remain untouched in memory. This leads to better cache utilization and faster performance. Trade-off: accessing all the data for a single entity becomes less efficient. SOA excels when you're iterating over all entities and performing the same operation on a specific subset of their attributes. 2. Data transformations, focus on the data flow. DOD emphasizes transforming data rather than encapsulating data within objects and calling methods on those objects. Algorithms are designed to operate on batches of data, example processing all entity positions in one go, to take advantage of SIMD, single instruction, multiple data, instructions and data parallelism. 3. Cache friendliness locality of reference organize data so that related data is stored close together in memory. This increases the likelihood that when you access one piece of data, the surrounding data is also in the cache. SOA promotes spatial locality for specific attributes. Padding and alignment be aware of how compilers pad structures to ensure proper memory alignment. Padding can introduce gaps in memory, reducing cache density. Consider reordering structure members to minimize padding. Understand and use compiler directives, example pragma pack, with caution. Incorrect use can lead to alignment issues and potentially crashes. 4. Minimal indirection avoid excessive pointer chasing. Pointers introduce indirection, which can cause cache misses. SOA, when properly implemented, reduces indirection compared to many object-oriented designs. 5. Separate data and logic in DOD, data structures are primarily containers for data. Logic is implemented in functions that operate on these data structures. This separation makes it easier to reason about performance and to optimize algorithms. Code example, entity movement in 2D. Let's illustrate the OWS versus SOA difference with a simplified example of moving entities in 2D. OWS, array of structures. SOA, structure of arrays. How to compile and run, using GCC. 1. Save the OWS code as OWS.c and the SOA code as SOA.c. 2. Compile *. 3. Run *. Observations and analysis. Performance *. You should observe that the SOA version generally performs better, especially as the number of entities increases. This is because the update entities SOA function only needs to access the X, Y, Vx, and Vy arrays, leading to better cache utilization. The OWS version, in contrast, brings in the entire entity AOS struct for each entity, even though only some of the members are used. Memory layout *. The key difference is how the data is laid out in memory. In OWS, all data for a single entity is contiguous. In SOA, all X coordinates are contiguous, all Y coordinates are contiguous, and so on. More advanced DOD techniques. 1. SIMD, single instruction, multiple data. Modern CPUs have SIMD instructions that allow you to perform the same operation on multiple data elements simultaneously. Compilers can often automatically vectorize loops if the code is written in a way that is amenable to vectorization. SOA is generally more amenable to vectorization than OWS. Use compiler intrinsics, example _mm_add_ps in x86 intrinsics, for fine-grained control over SIMD operations. This requires more in-depth knowledge of the target CPU architecture. Important notes for SIMD *. Compiler support *. Make sure your compiler supports SIMD instructions. GCC and Clang typically have good support. Target architecture *. Choose the appropriate SIMD instruction set for your target architecture, example SSE, AVX. The example uses AVX, Advanced Vector Extensions, which can process 4 floats at a time. AVX2 and AVX512 can process even more. Alignment * For best performance, align your data to the SIMD width, example 16 bytes for SSE, 32 bytes for AVX. Use _mm_load_ps and _mm_store_ps if your data is guaranteed to be aligned, otherwise, use _mm_load_ps and _mm_store_ps for unaligned loads/stores, but be aware of the potential performance penalty. Intrinsics SIMD intrinsics can be complex. Consult your compiler's documentation and the Intel Intrinsics Guide for details. Auto-vectorization compilers can sometimes automatically vectorize simple loops. However, for more complex operations, you may need to use intrinsics to achieve optimal performance. 2. Entity Component System, ECS. ECS is an architectural pattern that's highly compatible with DOD. It decomposes entities into their fundamental components, example position, velocity, health, renderable. Systems operate on components, processing large batches of data efficiently. ECS naturally leads to SOA-like data layouts. Explanation of ECS components position, velocity, health are simple data structures. They don't contain any logic. Entities are just identifiers, in this case, integers. They don't store data directly. Systems movement system and damage system are functions that operate on components. They iterate over the entities and process the components that the entity has. Asterisk component masks asterisk has position, has velocity, has health are Boolean arrays that indicate whether an entity has a particular component. This allows the systems to only process entities that have the necessary components. Asterisk SOA asterisk the component arrays, example positions, velocities, are organized in a SOA fashion. Asterisk flexibility asterisk ECS is very flexible because you can easily add or remove components from entities. This allows you to create a wide variety of entities with different behaviors. 3 Arena allocators, memory pools. Asterisk allocate memory in large blocks, arenas, instead of using malloc and free for individual objects. Asterisk arena allocators reduce memory fragmentation and improve allocation speed. Asterisk useful for allocating data structures that have a limited lifetime, example temporary data structures used within a frame. Key advantages of arena allocators asterisk speed asterisk allocation is very fast, just incrementing a pointer. Asterisk fragmentation asterisk reduces memory fragmentation because allocations are contiguous. Asterisk easy cleanup asterisk you can free all the memory allocated from an arena at once by calling arena clear or arena free. No need to track individual allocations. When to use DOD. Asterisk performance critical applications asterisk game development, physics simulations, high performance computing, real-time systems. Asterisk large data sets asterisk when you're processing large amounts of data, example thousands or millions of entities. Asterisk specific bottlenecks asterisk when you've identified memory access as a performance bottleneck. When not to use DOD. Asterisk small projects asterisk the complexity of DOD may not be worth it for small projects where performance is not critical. Asterisk rapid prototyping asterisk DOD can require more upfront design effort. It may not be suitable for rapid prototyping where you need to iterate quickly. Asterisk code readability / maintainability trade-off asterisk DOD sometimes can result in code that is less readable and harder to maintain than object-oriented code, especially if you're not familiar with the techniques. However, with careful design and documentation, you can mitigate this. Strive for clarity. DOD in other languages. While C is often the language of choice for demonstrating DOD principles, the concepts are applicable to other languages as well. Asterisk C++ asterisk you can use C++ for DOD, but be mindful of the overhead of object-oriented features if you're not careful. Use plain structs, avoid virtual functions, and use templates for generic programming. Libraries like Eigen can help with SIMD operations. Rust's ownership and borrowing system makes it well suited for DOD. It allows you to write safe and efficient code without the need for garbage collection. Java/C while these languages are primarily object-oriented, you can still apply some DOD principles, such as using SOA data structures. However, the garbage collector can make it harder to control memory allocation and avoid pauses. Conclusion: data-oriented design is a powerful paradigm for optimizing performance by focusing on how data is organized and processed. It requires a shift in thinking from object-oriented design, but the potential performance gains can be significant in the right circumstances. By understanding the principles of SOA, data transformations, cache friendliness, and minimal indirection, you can write code that takes full advantage of modern CPU architectures. Remember to profile your code to identify bottlenecks and to measure the impact of your optimizations. Good luck.